How are my peeps online doing? You're the only one here, Sarah. Keith was here. He left. He wanted to go study what's being tested on. How you feeling, Lauren?
I'm slowly feeling better. I'm hoping to be back on Thursday.
I hope you feel better soon. Are we on 26, 25?
26, I think.
So this is gonna be support work for 15 point, oh fuck it, chapter 15 in general. There's no reason to say at this point a specific one. We're looking at something called sequences and series. Okay, so what are they? Sequences are a list of numbers in order. I could have something like 1, 4, 7, 10, 13, and go on. This is called a sequence. In math, that's a sequence. Series is if I add these together. Okay. So like what we do in mathematics is this. Is there a pattern in the sequence? We focus on the sequence and go from there. Do you guys see a pattern in this? What do you mean by 3? We're adding 3 each time, yeah. Each number adds 3 to the previous. It's not always easy to recognize, but one thing you can do to see if there is a pattern like that where it's just adding is subtract consecutive terms. 4 minus 1 is 3, 7 minus 4 is 3, 10 minus 7 is 3, 13 minus 10 is 3. So each time it's going up by 3. Okay. So like, if we call, I'm gonna write this as a list of numbers. Like, so let's say this is the first number, and it's a 1. And the second number is 4. And the third number is 7. Fourth number is 10. Fifth number is 13. Is there a way to like find out the 98th number without adding 3 a shitload of times? That's what we're doing in mathematics. So that's like the goal, or one of our goals. figure out how to do this quickly. I got that new summer berry refresher. With lemonade from Starbucks. It's pretty fucking good. I'm not normally a raspberry kind of person, but. Blue raspberry with lemonade and fucking little red raspberry boba pearls.
Are they like popping boba pearls?
Yeah. Little tiny little pearls too. Really good.
Interesting.
I don't remember seeing it on the menu on Saturday or Sunday when I went, so like this is the last day or two. I skipped my chocolate cold brew to try it.
Sacrilege.
Hey, right? It is damn near sacrilege. But if I don't skip it ever, I'm never gonna try it.
What's the little sacrilege in this class?
Well, when you got someone like a avowed atheist leading the class, you're bound to have some sacrilege. All right, so what I'm gonna do is, let's call like, this is the 98th term, but let's call like one in the middle, like the nth term. So if like we can figure out a formula. Find a formula for the nth term. Finding the 98th or the 98,000th is really easy. Now, why would you want the number in the sequence that high? I don't know. There are some renowned sequences that, well-known sequences that are actually important in a lot of things, like the Fibonacci sequence. Shows up a lot in nature. So this is how one way we're gonna go about doing it. So I'll write down my list of numbers. You know what? Yeah. Yeah, we'll go with that. And maybe I'll add some more if I need some more. Throw them in. So if this is the nth number, I'm gonna call this the a sub n term. The nth number leads to the a sub nth term. This comes from writing a sequence as a function. F of n, we'll call it a sub n. So when you stick in n, you get a sub n. If I stick in n equals 1, I get 1. If I stick in n equals 2, I'll get 4. So maybe I should make that column like that. Call this n. This is a sub n. So this is like a sub 1. If n is 1, the first term is a sub 1. And that's 1. This one will be a sub 2. This one is a sub 3. And I'll just go through and label the ones I have. Okay, once I have that. If I wanna find a pattern and write it as a pattern. A good way, especially when it's an adding pattern, like Sarah identified, we're adding 3 each time. I'm gonna show this as being 1 plus 3. And I'm gonna show this as being 1 plus 3 plus 3. There's a reason to this madness. 10 would be 4 of them, or 3 of them. It's 3 plus 3 plus 3 plus 3. And what happens when I have repeated addition? What's a simpler way of writing this?
It would be power. You could write it into like.
Not a power, power is repeated multiplication.
Just multiplication.
It's just multiplication. So this would be like 1 plus 3 times 4. Because there's 4 3s. And this would be 1 plus 3 times 3. And this would be 1 plus 3 times 2. 1 plus 3 times 1. If I wanted to keep with the pattern, I would go 1 plus 3 times 0, right? So here I don't need to write it out, I can see where this is going. What if we go down and I'm down to the nth term? Is it n now?
Oh, it's 1 plus 3 times n minus 1.
It looks like we're off by 1, right? This is 0, this is 1. When n is 2, we're doing 1. When n is 3, we're doing 2. We're off by 1, we're down 1. So I could say that. Let's just verify that works. I'll call this f sub n or a sub n. If I want a sub 7, can I plug in 7 and get 19? We got 19. That's what we're looking
No,
for.
1 plus, yeah. 3.
This kind of wraps up. I just gave you a quick summary of what 15.1 and 15.2 is about.
Yeah, I was gonna say, I'm like, yeah, the power problem, yeah, this had always messed with me, because I'm like,
Wait, I wrote 1 plus 19.
I was gonna say,
That's what you were looking at me all funny for.
yeah, I was gonna say, I'm like, but this is interesting, because like. I always was confused by this, because for some reason I've never just skipped this part. I don't know why.
A lot of textbooks, a lot of teachers skip the thought pattern that goes into developing the formula.
Yeah, I was gonna say, I'm like, this wasn't in there, and I'm like, yeah. It's old.
In fact, you're gonna see, this is when we're doing 15.2. What number is the 1 on the a sub n list? What number is this right here? It's a sub 1.
Yeah.
What is the 3 here?
So,
The 3 is, I mean, the 3 going from each step. The 3 going between each step is called the common difference. I'll say that again in 15.2. The common difference is D, it's literally a sub n minus a sub n minus 1. Pick any 2 numbers in a row, subtract them. If it's the same number every time you do it, it makes this an arithmetic sequence. If this is the same every time. Or for every pair? This sequence is an arithmetic sequence. Maybe I'll change colors so it stands out a little bit better. In our problem right there, the common difference was the 3. Which in my formula right there is that. So. This is actually a formula for an arithmetic sequence. And we just came up with it by hand. Turns out when you're working with this kind of stuff, the hardest part is often finding the formula or whatever it is for the sequence you're working with, if there is even a formula.
How did you go? Yeah.
Yeah,
I feel like I always see it and then I'm like, I don't know how to write that.
right.
Yeah.
Not every sequence is arithmetic. Rather than waste paper, let's do it right here. What about? 1, 2, 4, 8, 16, 32, 64. What's going on from step to step here?
Square.
It's not squaring.
Or
Squaring would be 1, 4, 9, 16. Let's look at that. We'll do both of those. That's a good sequence as well. Oddly enough, some of these things are on both lists. The 4, the 16, the 64 are on both lists.
well, so wouldn't that first one be AN equals 1 plus or 1 times 2 n to the n?
So is this 1 times 2 to the n? That's Davis's theory. Where are you getting the 2? Let's break down what's going on here.
Or actually,
Let's do it first. I think you've noticed that it's off.
yeah, I noticed it, but yeah, that's
So where are you getting the 2 here?
because it's 2, 4, 8, 16, 32, and 64 are all different exponents of 2.
So it's all, we're multiplying by 2 each time.
Yeah, you multiply by 2.
Let's do what we did up here with this. Let's do something like that here. So I'm gonna say, and I don't think we need as many. That's a sub 1, I'm gonna, cause seeing the numbers kinda. The subscript is the n. It tells you which term you're on. And the same kind of thing, I'm gonna write it out. Doing what I did before. And then we'll shorthand notation it. And it feels kind of silly just to write 1 times it, anything times 1 is itself, so why don't we just skip straight to it and go, there's 4 2s. And they're multiplied, not added, so repeated multiplication is exponents. And I can do this as 2 to the 0. So what's gonna happen with the nth term? When n is 5, our exponent is 4. When n is 4, our exponent is 3. It looks like it's off by 1 again. This looks like it's 2 to the n minus 1. Does that work? The 6th term should be 32 and the 7th term is 64. If I say this is f sub n, f sub 6, not 6 sub 6, f of 6 is going to be 2 to the 6 minus 1. 2 to the 5th power is 2 times 2 times 2 times 2 times 2. That's 8 times 4 is 32. And f of 7 is 2 to the 7 minus 1. It's 2 to the 6, which is 2 cubed times 2 cubed. 8 times 8 is 64. So we are getting, it's following the right pattern. When you have it where it's repeatedly multiplied, repeated multiplication only, we tend to call these geometric series. And we'll be working more with this on Thursday. This is 15.3. But I wanted to make it clear, there's more than one type of series. It's not all arithmetic. 15.2, we're going to do a lot more with arithmetic sequences and series. 15.1, we're just going to be focusing on sequences in general, so we're going to explore a whole bunch of shit. Any questions so far? How about you guys online?
Doing good.
All right. All right, all right, all right. We had the other one up here. 1, 4, 9, 16, 25, 36, 49, 6. I don't know why I looked at it. I know these numbers. Fuck. It's embarrassing that I grabbed that page and looked. So if you don't want to do the whole table thing, you want to speed this up.
Yeah.
What we're going to do is we're going to, like, say it's a space. We're going to call this a sub n, and we'll write the n's underneath it. Now I don't have a whole table. And if I look for addition between them, it's changing. From here to here, it's 3. From there to there, it's 5, 7, 9, and it actually keeps going up by 2. That's not something we want. And if I look for a multiplier or anything like that, it's not there either. These are squared numbers though. A sub n turns out to be n squared.
Yeah. So, yeah.
So these are along the diagonal of a multiplication table. And those are the perfect squares. Some patterns are really hard to spot. If I had 0, 3, 8, 15, 24, 35, 48, 63. It's a little hard to spot. Because there's no, like the addition is changing each time, so it's not addition. The multiplying 3 times 0, there's nothing times 0 that'll give me a 3. So it's clearly not just multiplying. And if you get lucky toying around with it, you'll notice they're really close to this. This is actually n squared minus 1. So not easy to spot.
So you could. So we haven't even gotten to something to the end. We haven't even gotten there yet.
You should there right here.
Oh, yeah, no, I'm wrong.
It's to the n minus 1.
Yeah, so it's. This-
Something that shows up a lot in these sequences and series are called factorials. It's written with an exclamation point. A number or variable followed by an exclamation point. I'm gonna write it with a number first, because it's a little easier to go, oh, no shit, that's what it means. So 5 factorial, that's how we would say it, 5 factorial.
That's what the exclamation point means.
Yes. You keep multiplying by a smaller number until you get down to 1. That's how we define it.
Oh. Okay.
So n factorial, if I were to try to write a formula, it would be n times n minus 1 times n minus 2 times dot 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 3 times 2 times 1. So what would 7 factorial be, Sarah?
7 times 6 times 5 times 4.
There we go. Pretty easy, right? This is not a complicated idea, but how does this relate to 5 factorial?
2 factorial is higher.
I could write this as 7 times 6 times 5 factorial. You may be like, why do that? Well, it turns out when we're wanting to compare things and there's factorials in both of them, it makes it a hell of a lot easier to cancel out a bunch of the factorials and get rid of the factorial symbol, because that's hard to wrap your head around. Like, what's going on with the factorial symbol, but if I can eliminate it.
But then so you can multiply in a formula by 7 factorial as if it's a normal number, kind of like pi or something.
Say that again?
But I mean, I'm like, if I know that if I have 7 factorial, that's not, I don't have x, the exclamation point, it's not a variable, it's.
Right, it's a fixed, now this is a calculatable number.
This is an exact.
I think 5 is 120. So 6 would be 720. And 7 is, I don't know, 50, 40, I don't know.
Yeah, it's.
It's getting up, they're getting high. Because the first few are easy. 3 factorial is 6, 3 times 2 times 1. 4 factorial is just gonna be 4 times 3 factorial, but 3 factorial is 6. So 4 times 6 is 24. 24 times 5 is 120. That's how I was doing it quickly in my head.
I was going top down.
There is something we have to note here. 0 factorial is defined to equal 1. Cause you're like, why not keep going? Why are we stopping at 1? It also turns out that one of the primary uses for this is in probability and statistics. And you end up having n minus n factorial, which is 0 factorial. And if you want to use the formula, we can't just have it be 0. So we define it to be 1 so that it. Knowing full well that 0 times anything is 0. But in terms for everything we use factorials for, we make it 1 because that'll make it suit our needs. So maybe simplify. Go ahead and give this a try. I would try to write it in terms of what's left over.
Yeah.
Rather than like any jackass can use a calculator. It's not gonna help you do these things later on. Right, recognizing what's left over, the parts of it.
If you just stretch it out, all the numbers, they're on the top and the bottom. They don't.
Right.
So it's 14.
Yeah, looks like it. You do that in your head? Good.
6 times 7 over 3. 6 times 36 and 7 are the only ones left on the top. And you just squish them together.
6 over 3 is 2, makes it a little bit easier. But you probably did 7 times 6, then divide by 3.
That's it.
14 divided by 3 isn't that easy in my head. I could do it, but I have to stop and think about it.
I just knew that 42 is 7 times 6, I divided 6 by 3.
Yeah, okay.
And times 2 by 7. Like,
So for each of these, I'm gonna take advantage of the factorial on the other side. I'm gonna write 3 factorial as 3 times 2 factorial. And I've got a 2 factorial on top. In this one, I'm gonna write the 7 factorial in terms of the 5 like we did on the page above. And we can see what cancels. Those cancel and those cancel. I'm left with 7 times 6 over 3. 6 is 3 times 2. Cancel the 3's and I get 7 times 2 is 14. And if you already have pencil and paper out and you do something like this is actually fucking quicker than digging out your fucking calculator and figuring out where the fucking factorial key is. You can actually do this faster. As long as the numbers don't get unreasonably large. But you'd be surprised how much shit cancels. Even doing that, like if when you're doing probability, like getting a poker hand. You've got 52 cards in the deck, you got 52 fucking factorials showing up in that motherfucker. But when you're canceling out fucking 49 of them, 50 of them. You're only left with a couple numbers left and they're divisible by 2 and 3, they'll get smaller really fucking quick. I cuss too much. Ooh, ooh, oh. All right, that was some factorial work. Let's look at it in terms of sequences. Mr. Jones, why you gotta do that shit? We were having a good time. Factorials were easy. I like it. Can we have the whole final meeting on fucking factorials? I mean, shit. Oh, no, yeah, I'll do this. Not, I don't want to do plus, that's series. Let's do commas. We'll cover series today. But the sequence stuff is the hardest part of it. They're so interconnected. Like almost every time you work with a series, it's like figure out what it is as a sequence first, because that's the easy shit. And once you have it, then the series becomes easy. So this is my first term, my second term, my third term, my fourth term, my fifth term. With more practice, you will get used to recognizing that is 2 factorial. 6 is 3 factorial. And then factorials don't change. They're fixed values. So once you've seen the first 5 or 6 several times in a row, hopefully you start recognizing it. So what would be a general formula for this sequence? Yeah. Because this is n equals 1, this is n equals 2. Yeah, I could write this as 1/1 factorial. Seems kind of silly. 1/n factorial. All right.
You couldn't have a negative factorial.
Oh, I'm getting ready to throw negatives in right now.
Okay, I was like.
But no, not negative factorial. We don't go down to a negative.
It's
not a factorial.
negative.
We count down to 1. And when you start working, when they're integers, they're always integers. Positive integers, strictly positive integers. 0 factorial, I guess we have 0, I guess we could say non-negative, but 0 factorial is just 1 anyways. It's the special rule case. When you start working with fractional factorials, there's something called the gamma function. And that was like graduate work for me, and I fucked that function. I don't remember, I remember not liking it. This is easy. And you're like, why can't it be easy with the other? No, it's, They gotta-
figure out how to make it easy.
right. Alright, so. I don't wanna throw the factorials in. Maybe I won't, well, maybe I'll just introduce the negative concept here. No,
It's the thing that we did.
you wanted to call it square root that time too.
Yeah.
So Lauren, can you see what's going on here? In this pattern?
Is it multiplying by -3?
Looks like I might be doing -3. So let's just like line these up. With their terms. So this is like -3 to the first power. This is like -3 to the second power. -3 to the third power. -3 to the fourth power. So this looks like it's gonna be. If I go downwards, this is -3 to the 0 power. It looks like we're off by the one again, and -1. And I'm gonna point out something to you that hopefully you know, but haven't really thought about. I can write that as -1 to the n-1 power times 3 to the n-1 power. And the reason why I say that is we see this a whole lot more. This -1 to the n or -1 to the n-1 causes a sequence to alternate signs. That actually leads us to calling them alternating sequences or series. Alright, so different color. Find the pattern there. Write the shortcut notation for this. I thought boba things were supposed to be like tapioca pudding or some shit like that.
No, they're just gel.
It's just a gel capsule for any filling.
I thought it was,
It's a gel.
it's somewhere in the middle. Sometimes it's like that.
Oh, yeah.
Like the more like traditional places like that, but sometimes it's not.
Where how they make them?
Whatever the black ones are, they're like that. But sometimes there's all.
I think you just like boil some water first. Then get the ingredients, they like drop them in there individually and then scoop them out. And something like that.
Well, they're like filled, like how do they get the, is this,
It's their gel, like it's.
right, but how do they get the liquid inside the gel? Because I know, I pulled out a bit. And the gelatin is fucking clear, so it's not the same color as the fucking liquid inside. So I don't know that it's just they dropped a ball of fucking liquid in and the outside fucking solidified.
There's two types. Those are popping like fruit boba, but the tapioca pearls like don't pop and they're chewy.
Are those any good? Cause
No,
I've never
they
tried them,
taste
cause in my
really good.
head, I don't wanna chew when I'm drinking.
Yeah, it's kind of a weird experience for sure.
Is
They
it
don't
good
taste
though?
very good. No,
Oh,
they
yeah.
don't
It's
taste
good? You like it, Lauren?
Yeah,
No, they don't taste good.
They don't taste good.
I do like, I like, but there's a good place for them, there's a good bubble tea place in Hampton. That is like in the downtown area.
I think I'm going to Hanford to try something that sounds disgusting.
You gotta go to Hanford to skate.
You know, I do like a Hanford, but they have them over here. Chilios tacos, Chilios number 2. Oh god, they fucking make fantastic tacos. God, oh man, it's like a mouth watering to think about it. They opened one up in Tulare and they're all right, but they're not as good as the Hanford branch.
I don't know, I'm loyal to some of like Colima's for burritos in downtown Minnesota and Hobby's tacos. So, I don't know.
Do they still have fried ice cream?
I don't know, I've never tried it.
Chilios is definitely better than Hobby's tacos, in my opinion.
I feel like Hobby's has gone down. When I was first here like a while ago, Hobby's was better. It was mega.
You don't even have, you said you haven't even had Chilios.
How
How do you fucking know that was better?
No, better.
I've had both and I'll tell you Chilios is better.
Hobby's in the past versus Hobby's now.
Oh,
That's
okay.
what I'm saying. Like that, but old Hobby.
Hobbies is, I haven't had them lately. I'm not saying I don't like hobbies. But I'm like, you kind of pay a lot for what the little you get.
Yeah, we've got.
And I feel like the Chilios tacos are much fatter, a lot more meat. Some fucking cilantro, some onion. Just go to town, thought of taco, okay. Do we have a pattern for this one? Or I fucking, so this is our first term, our second term. Fourth term or fifth term. We can address the signs and the numbers separately. Is this following -1 to the n or -1 to the n minus 1?
You're going to the end,
Why you say that?
because it would be, if it was just -1, it would be. The first -1/2 was negative, so it starts the first negative number,
First number is negative
not the second.
and odd number ends are negative. That works. It is -1 to the n. What about the number part?
You just denote it as 1/2, right? The fraction,
Sure,
it still works.
but what's the pattern for the number part?
Oh, it's still.
So we could say -1 to the n, 1/2 to the n. You generally won't see it like that. You'll see it like this. That's just to give you guys a little bit of sampling of all the shit and sequences we're doing. And I will hit stop record.